All right, let's jump right in. Today, we're diving deep into your research on something super cool, optimizing model and dataset sizes for embodied AI.
Cool stuff.
Right. You've been looking into how to get the most bang for your buck in AI, so to speak, making sure you're allocating resources right to squeeze every bit of performance out of those embodied AI systems.
Exactly. It's all about efficiency and getting the most out of the resources you have.
And your research is digging into something really fascinating. The relationship between model size, the amount of data you're feeding these systems, and the specific tasks they're tackling.
Yeah, and the results are pretty surprising, especially when you start comparing different approaches like behavior cloning versus world modeling. There are some definite aha moments in there.
Aha moments are the best.
They really are, especially in research.
Okay, before we get too far, let's do a super quick recap. For those just joining us, or maybe just need a little refresher, can you break down those scaling laws everyone keeps buzzing about in AI, and how do they play out in the world of embodied AI? You know, those AI systems that aren't just crunching numbers in a computer, but actually interacting with the real world, like robots.
Yeah, totally. Scaling laws, they're basically like a roadmap. They help us understand how the performance of an AI system changes as we scale up the model size and the amount of data we use to train it.
So bigger model, more data, better performance. Huh.
No, it's not always that straightforward, especially when we talk about embodied AI. Think about it like training a robot dog to fetch.
We're robot dog. Cute.
Right. Now, if you have a massive model but you only show it a handful of examples of fetching, it might become a super specialized fetcher, but only for that specific type of ball.
So it would only fetch tennis balls, not soccer balls.
Exactly. It's overfitting, not able to generalize to new situations. But if you use a tiny model and show it thousands of examples of fetching all sorts of things, it might get confused and not learn to fetch anything well.
Okay, so there's this balancing act between model size and data size.
Bingo. Scaling laws in AI, they help us navigate that balance to get the most out of our AI systems, whether they're robot dogs or self-driving cars.
Which, speaking of self-driving cars, that connects perfectly to what you're researching. This whole idea of optimizing resources is critical for those complex systems, right?
Absolutely. Resources are always limited, and you want to use them wisely. And what's super interesting is that your research shows this optimal balance, this ratio between model size and data, actually changes depending on whether you're using behavior cloning or world modeling.
Okay, back up a second before we jump ahead. For the folks tuning in who might not be familiar with those terms, can you give us a quick breakdown of behavior cloning and world modeling?
Sure thing. Let's stick with your robot dog example. In behavior cloning, you'd basically be showing the robot dog a ton of examples of how to fetch. You demonstrate the desired behavior, and the robot learns by imitating those examples.
So it's like learning by watching.
Exactly. Now, with world modeling, things get a bit more complex. It's like building a virtual playground for your robot dog inside the computer.
Oh, like a simulated world where the robot dog can practice fetching.
Precisely. The AI gets to explore, experiment, and learn the rules of the environment in this safe, simulated space.
This is blowing my mind.
So we've got these two distinct methods: behavior cloning, where the AI learns from examples, and world modeling, where it learns by interacting in a simulated environment.
And you're telling me that the magic formula for optimizing resources is different for each method.
That's exactly what your research highlights, and this is where it gets really exciting. For behavior cloning, a larger model can actually be more effective, even with a smaller data set.
Hold on, I need to wrap my head around this. So you're saying that for certain tasks, instead of just gathering mountains of data, focusing on a leaner, more powerful model might actually give us better results.
That's the surprising insight, and it has huge implications. It means that researchers can potentially save a ton of time and resources.
Imagine that. Not having to spend weeks collecting data when a smaller model could have done the trick.
Talk about a game changer. But it's important to remember that for world modeling, a massive amount of data is still crucial for the model to truly excel.
Got it. So different tasks, different recipes for success. But the big takeaway here is you don't always have to go big or go home when it comes to both model size and data size.
Right.
You got it.
It's about finding that sweet spot, that optimal balance for each specific application. You've got to think strategically about which tasks need what kind of resources.
This is incredibly valuable information for anyone working with AI, especially in robotics and those complex tasks like building self-driving cars.
Absolutely. Understanding these scaling laws is a game changer for how we develop and deploy embodied AI in the real world.
And it leaves us with a lot to think about, like how might these findings shape the future of AI development, especially in fields like self-driving cars or even robot assistants?
That's a great question to ponder. The possibilities are truly mind-boggling.
Well, on that note, huge thanks for joining us on this deep dive. We hope this has sparked some new ideas and insights for you to apply in your own work. Until next time, keep those AI wheels turning and happy researching.